Hello all, welcome to the video series on SIPI by E for Engineer. In the last video, we have seen the causes of signal integrity problems and had a detailed discussion on signal integrity of one net. We came to know that the signal quality of a net primarily depends on the electrical properties of its trace and the discontinuities and impedance it sees. So now in this video, let us focus on crosstalk. So what is crosstalk? So to understand it better, let us take an example. So here we have line A in blue color and line B in red color. Let us take this red color to be a quiet line, and there is no signal transition or activity observed in this red line. So when the signal travels along this blue line, it can see some discontinuities and it triggers voltage and currents changes. So when the signal is traveling and the currents or voltages are changed, then it results in the change of electric and magnetic fields surrounding the signal. So when the electromagnetic fields change, it results in coupling, and some voltage or current is coupled to the quiet line, which is red line. This phenomena we call as crosstalk. Why do we call it so? Because this red line being the quiet line, it is expected not to observe any activity on this line, but since some changes are happening in this line A, and because the coupling has happened, this red line also sees some amount of voltage and current which is unwanted, and that unwanted noise we call it as crosstalk. And this crosstalk can be two types. It can be capacitive coupling or it can be because of inductive coupling. So if we talk about capacitive coupling, suppose say here we have one signal trace and nearby we have another signal trace. When the voltage from the first trace gets coupled to the other trace, then we call it as capacitive coupling. So it is nothing but because of the voltage changes in the first trace, the charge will be induced in the second trace, and this phenomena we call it as capacitive coupling, and the corresponding crosstalk we call it as capacitive crosstalk. So now let's come to the second phenomena, which is inductive coupling. So this is the first trace, and because of either the discontinuities or non-uniformity in the signal, there will be some currents change. Because of this, magnetic fields also change, and these magnetic fields will induce the currents in the side by or adjacent trace, and this we call it as inductive coupling. So basically, because of either capacitive coupling or inductive coupling, the crosstalk is generated. Now let us see how this crosstalk will be in two different environments. Here we're gonna discuss about uniform transmission lines and non-uniform transmission. We have examples for transmission lines, that is a twisted pair, a coaxial cable, a microstrip line or strip line. These are all transmission lines and they can be uniform or non-uniform. Basically, a transmission line is a signal along with its written path. A pair of traces are called transmission lines. So now let us talk about how is the crosstalk in uniform transmission lines. So in uniform transmission lines, the topology of the signal trace will be constant from transmitter to receiver. So if we take this line A, and if it is a uniform transmission line, then its topology, that is the electrical properties and the physical properties like the signal width, the written path width, the spacing to the other signals, everything will be constant all along its length. Then in that case, we call a particular transmission line as uniform transmission line, and it will be having its impedance as constant. So in that case, we'll be having the capacitive coupling and the inductive coupling, both are comparable, and in this case of uniform transmission lines, there will be less issues in crosstalk. That is, the crosstalk is manageable. But in the second case, which is uniform transmission lines, there the inductive coupling will be more because there will be too many discontinuities. That is why we call them as non-uniform transmission lines, and because of this, currents change. So as a result, the inductive coupling will be more dominant than the capacitive coupling. So when the inductive coupling is dominant in any transmission line or in the crosstalk phenomena, then the noise created by that coupling or that crosstalk which is dominated by inductive coupling, we call it as switching noise or delta I noise noise, or DI over DT noise, or ground bounds, or simultaneous switching noise, or simultaneous switching output noise. So these are the terms used to define that particular kind of crosstalk. When this coupling happens, we call that inductance as mutual inductance. So when two traces are there, there will be mutual inductance between them, and because of this mutual inductance, this SSO will get generated, and this is nothing but inductively coupled crosstalk. So now we have seen what is the crosstalk and how the crosstalk is generated. Now let us see some ways to reduce the crosstalk. So these are very popular ways to reduce crosstalk. The first one being to space apart the traces, meaning we should increase the spacing between the signal traces, which lowers the crosstalk. And we can try using a lower dielectric constant material, and we can also try to decrease the interconnect length. So in this video we have discussed briefly what is crosstalk, how it is generated, and what are the ways to decrease crosstalk. And in the coming videos we will try to address, or we will try to discuss the remaining categories, that is rail collapse and EMI issues. So that's all for this video. If you have any doubts, please visit logicsoc.com, or you can mention in the comment section as well. Thank you so much for watching, and stay tuned to E4 Engineer for more videos.